Hi, I'm Andre and I'm going to present YaCoS, which is a framework to explore the compiler optimization sequences and design learning models for predictive compilation. This is a joint work with Anderson and Fernando. We can see in this chart a simplistic representation of predictive modeling. This technique has the property that it tries to learn a model that describes with accuracy the correlation between inputs and outputs. In predictive compilation, we have a dataset of benchmarks for training, and we want to test the model within new programs. The learning process usually involves the compiler through performance compilation, execution, and extraction of features from the benchmarks. These features can be any information related to the program, such as number of load instructions or function calls. The target of the predictive compilation can be a continuous or discrete value, such as execution time or number of instructions. One of the main obstacles to the adoption of predictive compilation is the size of the search space. A sequence of optimizations or transformations can allow repetition, and the relative order of application matters. Two sequences with the same optimizations can produce different results according to the order of their elements. This command line shows some optimizations of the compilation plan O1 from LLVM9 in my machine. This is just a fraction of all the available transformations, which is a few hundreds. And we can see that in this compilation plan, there's a lot of the same transformation. In this image, you can see a three-dimensional feature space formed by the number of stars, number of instructions, and the depth level of the innermost natural loop in the program. The elements of the vector are determined by the applied optimizations, as we can see in the circled points. This image shows how the key nearest neighbors algorithm can be used to predict the best optimization tuple for an unknown program based on its future vector. The circled points show the most closed programs of our test program based on their future vector distances. We can see in this image on the right how the algorithm can fail in prediction due to undiscovered regions in the future space. It means that in these regions there are unknown programs and the training process of the model was unable to cover the entire space. Machine learning techniques has been adopted for a plenty of tasks in different fields. This occurs due to the fact that there are well-established open-source machine learning frameworks available in programming languages like Python. In order to make good models, a large number of training data is required. In this case, a large number of benchmarks. This fact is actually a challenge in this field, since a lot of benchmark suites doesn't have much more than a few dozens of programs. This scenario starts to change since we have now code synthesizers and open source miners, such as CLGen and Anga, which is capable of generating thousands of benchmarks. We also have the ascension of open source, where we can rely on different compiler implementations such as LLVM and GCC, and we have different programming frameworks for testing for predictive compilation, like OpenCL. The most similar project to ours is the YaCoS GCC, which is one of the most well-established frameworks for predictive compilation for the C programming language. Its components are made of a feature extractor, which collects 56 different static features, a set of programs for training, and metrics for similarity measured between these programs. YaCoS records how each sequence performs and has been used for runtime and code size optimization. However, we believe that YaCoS suffers from a shortage of benchmarks, with only CBench being distributed in this project, and also it's restricted to an old version of GCC, the GCC4. To overcome these issues, we propose YaCoS, which is a complete framework for the design of predictive compilation models. The infrastructure has a rich set of benchmarks formed by 5,000 of C-compilable programs and 300 complete benchmarks that can be used for training and testing. Just like YaCoS, YaCoS has a feature extractor, but with a much larger number of features and distance metrics, not only with static features, but also dynamic, making several combinations possible. The search engine has multiple algorithms to smartly search the vast space, and in combination with different compilation strategies, makes YaCoS suitable for the design of experiments. All components of the infrastructure uses the LLVM compiler. We believe that LLVM enjoys more the support of the research community, and several adaptive techniques are now implemented in this compiler. Now let's move forward and explain each component. As said before, the program filters are classified as static and dynamic. The static filters are implemented as LLVM passes that operates in the LLVM intermediate representation. Therefore, all static filters are information related to this code. The LLVM optimizer is the tool that performs the analysis on this representation. We have the MESF pass that are the 56 filters of milepost but implemented in LLVM. It encompasses characteristics of the control flow graph and instructions, such as number of basic blocks. The loop paths are composed of 17 filters related to loop data and control dependencies, such as read after write and write after read data dependencies. The LLB path derives its filters from the bitcode analyzer. We call an LLVM bitcode an encoding of the LLVM intermediate representation in a string of bits. These encoding instructions includes elements such as blocks and data records. LLVM also provides developers with statistical information, which can be optionally printed as the result of the execution of a transformation path. The LOS does this job. For example, it requires the number of eliminated instructions in a constant transformation path, as we can see in this code after the application of the const property transformation. Finally, we have an encoder that transforms each instruction in a unique symbolic representation. With all these paths, we have more than 200 static filters available for use. The dynamic extractors are pin tools. A pin tool is a plugin that can be loaded by the pin binary instrumentation framework of Intel. We have the CAT tool, which collects the number of instructions of the hardware instruction set, such as Intel AVX instructions. The jump extractor, that counts number of calls, indirect calls, and everything related to jump instructions. The LDST gets the memory-related instructions like reads and writes. Mika is a collection of microarchitecture independent filters. It is capable of measures for the entire execution or per interval of dynamic instructions, as we can see in the interval size in red. It also allows different analysis types, like instruction level parallelisms or instructions related to registers, like the average number of register operands. We also make use of perf to measure performance counters related to CPU and memory. Finally, we collect 15 performance counters from PAP. Information about the cache are some of those contemplated in this set. For dynamic filters, we also have more than 200 filters available. The search engine is used to associate good optimization sequences with programs. Basically, it's a mapping performed by an algorithm from the dataset of benchmarks to good optimization sequences. YaCoS provides several search methods, like particle swarm optimization, evolutionary algorithms, active learning for minimization of the number of executions of the application, which can be very costly. We have case-based reasoning search and algorithms that is capable of sequence reduction and harmful sequence elimination, which are sequences that slow down the application. YaCoS also provides a collection of adjustment parameters for most of the search algorithms. For instance, the genetic search algorithm is parameterized by its definition of population, generation, dimension, and training data. The program's distance is a measure of similarity of programs. It is calculated based on the program's future vectors. Programs close to each other must be treated in the same way by the model, so it can make accurate predictions for unknown programs. The M coefficient measures the distance between two programs as the effect of a sequence of optimizations onto these programs. The behavior is understood as the performance speedup or slowdown provided by the optimizations, in case runtime is the objective function, or code size reduction in case code size is the goal. Another distance is given by a DNA alignment, where for each optimization is given a unique symbolic representation, and then the Needleman-Wunsch algorithm, which is widely used in bioinformatics, does a sequence alignment in the future vector, assigning a score between different sequences. YaCoS also calculates the well-known Euclidean, Cossini, and Manhattan norms. Here we can see how these norms are computable, where px and py represents the numerical future vector of the sequences x and y respectively, applied to the program P. A compilation strategy determines which optimization sequences are applied onto the unknown program. YaCoS has three main compilation strategies for selecting the best optimization sequences. The first one is the elite approach. Each works with a baseline compilation plan like O1 or O2, and then the elite approach selects only the best sequences compared to the baseline performance to be propagated in the search. Given a subset of sequences and a positive integer x, the JX strategy chooses to apply only these x best sequences onto the unknown program. The GX approach is similar to J. Given a subset of sequences, we apply only the X good sequences. By good, we mean the sequences that is better than the baseline sequence. The objective function is the function in which the search algorithm tries to minimize or maximize. It can be a static function, for example, a function to minimize compilation time or code instructions, or it can be a dynamic function, where these functions are computable by running the program and profiling its behavior with perf, LLVM MCA, or hyperfin. Examples of these dynamic functions could be execution time or number of CPU cycles. We say multi-objective function because you can assign weight values in the interval 0, 1 to each objective goal, as we can see in the multi-goal function. YaCoS contains two benchmark suites. The first one is the Anga benchmark, which consists of 5,000 C benchmarks mined from open source repositories. These benchmarks are compilable but not executable. The second one is the LLVM test suite with 300 executable benchmarks with different sizes of predefined inputs by YaCoS. To show how YaCoS works, we did some experiments using all components of the infrastructure. We used 1,200 Anga benchmarks for training, 300 Anga benchmarks for testing. We used all the three compilation strategies with different values of x. Our baseline was Clang OZ, which is a compilation plan for code reduction. And in our objective function, we try to minimize the size of the program, measured in number of instructions. This experiment only differs with regard to the filters used to represent programs. Since we want to minimize the number of instructions, we only use the static filters. These are the milepost static filters, the milepost plus the loop filters, and the LLVM statistics filter set. This blue graph labeled full shows the mean absolute code size variation for the 300 programs, which is the mean variation in the number of instructions for each compilation strategy. Most of these numbers, with the exception of G1, are negative. That means that OZ performs better at average. This occurs due to the fact that this compilation plan is a well-established optimization sequence, with many years of effort from different compiler experts. However, in several programs, YaCoS has been able to outperform OZ. The green graph summarizes the mean value only in the programs in which YaCoS has been able to find a sequence that improves the baseline. These green numbers shows the number of benchmarks with better sequences found by the system. We can see in J100 that we have a mean of 10.52 instructions less than OZ and 122 programs with better sequences. The red graph shows only the best reduction provided by a sequence found by YaCoS. In this case, the G100 was the best approach. Now let's show in this table the percentage of code size variation. We will be looking only at the programs with better sequences than Clang OZ. This line shows the number of programs that outperforms OZ. These are the same numbers shown in the green graph, where the J100 gives us the best number of programs with better sequences. This line shows the max improvement in percentage. The difference of 35.19% corresponds to a reduction of 254 instructions in one program. And here we can see the mean improvements. Now let's compare with the other filters sets. The results for YaCoS plus LUP yields a slightly better result for a number of programs, but still the mean are quite similar, so we cannot say for sure that the additional features improves the prediction. The same behavior occurs with LLVM statistics, where the results are practically equivalent to those earlier reported. In all the cases, we have been able to achieve a code size improvement of about 3.5% over the baseline. We have shown that YaCoS is a versatile infrastructure and we can beat standard compilation plans in a pretty good number of programs. As future work, we plan to continue to expand the infrastructure to accommodate more features and more algorithms, such as neural networks. Thank you.